Welcome to AI Frontiers, the podcast where we explore cutting-edge research shaping our technological future. Today we're examining a fascinating collection of studies from August 15, 2025, that reveal both the incredible promise and unexpected challenges of modern artificial intelligence. Picture this: you're playing chess against a grandmaster, but instead of making moves yourself, you have an incredibly knowledgeable friend whispering suggestions in your ear. Sometimes they give you brilliant strategic insights, other times they confidently suggest moves that would lead to immediate defeat. This is essentially what's happening right now in the world of artificial intelligence. This chess grandmaster paradox perfectly captures the current state of AI systems. These systems can be remarkably intelligent, yet surprisingly flawed in ways that mirror human cognitive biases. Modern AI is like having that knowledgeable friend suggesting chess moves, sometimes providing brilliant strategic insights that lead to victory, and other times confidently recommending moves that result in immediate defeat. What makes this particularly intriguing is that AI systems exhibit cognitive biases remarkably similar to those observed in human decision-making. This discovery challenges the fundamental assumption that artificial intelligence is inherently more rational or objective than human intelligence. The central question becomes, how do we harness the remarkable intelligence of these systems while avoiding the potentially fatal pitfalls they can introduce? The 8 groundbreaking studies we're exploring today go far beyond incremental improvements to existing technology. These represent fundamental insights into how we can make AI systems more reliable, more useful, and more aligned with human needs. The research spans from theoretical frameworks that explore the mathematical foundations of intelligence to practical applications that solve real-world problems. What distinguishes this work is its focus on moving beyond artificial laboratory tests to understand how AI systems perform in natural, messy, real-world contexts. The overarching theme involves understanding how AI can collaborate effectively with humans rather than simply replacing human intelligence. These studies reveal an AI landscape that's more nuanced and more human-like than previously imagined. Think of the field of computer science artificial intelligence as a vast digital ecosystem, much like a rainforest where different species have evolved to fill specific niches. Just as a rainforest contains everything from towering trees that reach towards sunlight to fungi that decompose fallen leaves, the AI research ecosystem encompasses theoretical frameworks that serve as towering trees reaching toward understanding, alongside practical applications that function like fungi, decomposing complex problems into manageable components. This ecosystem thrives on interdisciplinary convergence, drawing insights from psychology to understand human thinking, neuroscience to understand brain processing, mathematics for rigorous foundations, and engineering to build functional systems. Each layer contributes uniquely to our expanding understanding of intelligence itself. The first major research theme involves the integration of large language models with traditional AI reasoning systems. This represents a fascinating convergence that's reshaping AI architecture fundamentals. Imagine trying to combine the intuitive pattern recognition of an experienced doctor with the logical precision of a medical textbook. That's essentially what researchers are attempting. This integration isn't about replacing old methods with new ones, but rather creating hybrid systems that leverage the strengths of both approaches while mitigating individual weaknesses. Classical AI systems excel at logical reasoning and can guarantee finding optimal solutions, but they struggle with the computational complexity of real-world problems. Large language models can quickly generate plausible solutions based on pattern recognition and vast training data, but they lack the logical guarantees that make classical systems reliable for critical applications. The second prominent theme involves developing evaluation methodologies that better reflect real-world performance. Traditional AI benchmarks function like standardized tests, measuring specific capabilities under controlled conditions, but they may not predict how well a system performs when faced with messy, unpredictable challenges of actual applications. Researchers are increasingly recognizing the need for evaluation systems that capture the complexity and variability of real-world usage. This has led to innovative platforms that collect feedback from actual users interacting with AI systems in their natural contexts. The research reveals that AI systems evaluated using feedback from actual applications show dramatically different performance patterns than those evaluated on traditional benchmarks, suggesting that application-specific evaluation may be necessary to accurately assess true system performance. The third major theme centers on understanding and addressing cognitive biases in AI systems. As AI agents are increasingly deployed in business-critical applications, researchers are discovering that these systems exhibit decision-making biases remarkably similar to those observed in human cognition. These biases include framing effects, where the way a problem is presented influences the solution chosen, and anchoring effects, where initial information disproportionately influences subsequent decisions. This finding challenges the assumption that AI systems are inherently more rational than human decision-makers, and suggests that simply replacing human decision-makers with AI systems may not eliminate bias-related problems. Instead, it could potentially introduce new forms of systematic error that require sophisticated approaches to bias detection and mitigation. The key findings emerging from today's research reveal insights that could fundamentally change how we design and deploy AI systems. One of the most significant discoveries relates to the effectiveness of domain-specific knowledge in language model applications. While there's been tremendous excitement about the general capabilities of large language models, research reveals that their effectiveness is dramatically enhanced when augmented with domain-specific knowledge rather than relying solely on general world knowledge. This finding challenges the prevailing notion that bigger, more general models will inevitably outperform specialized approaches. Instead, it suggests that the most effective AI systems may be hybrid architectures combining the broad knowledge of foundation models with the precision of domain-specific reasoning systems. Additionally, research demonstrates that AI systems benefit from structured curricula like human education, and that adaptive architectures consistently outperform fixed designs in continual learning scenarios. Among today's standout papers, Inspire or Predict, Exploring New Paradigms in Assisting Classical Planners with Large Language Models, by you and colleagues, represents a particularly fascinating exploration of how different types of AI systems can work together synergistically. This research tackles one of the most fundamental challenges in artificial intelligence: solving complex planning problems involving enormous state spaces where traditional algorithmic approaches become computationally intractable. The research recognizes that classical planners function like master logicians. They can guarantee finding optimal solutions with transparent, verifiable reasoning, but struggle with computational complexity. Large language models operation like intuitive experts who quickly generate plausible solutions based on vast experience, but their reasoning is often opaque. The researchers developed two distinct operational modes. LM4INSPIRE uses general world knowledge for heuristic guidance, while LM4PRICT incorporates domain-specific knowledge for intermediate predictions. The framework validation spans multiple planning domains, including logistics problems, resource allocation scenarios, and scheduling challenges. The results reveal fascinating insights about when and how language model assistance proves most effective. Perhaps most surprisingly, the research demonstrates that effectiveness depends heavily on the quality of problem decomposition. When complex problems are broken down into well-structured subtasks that align with patterns the language model encountered during training, the assistance proves remarkably effective. However, when decomposition is poor or subtasks don't match familiar patterns, benefits diminish substantially. This finding highlights the critical importance of careful system design and suggests that successful integration of different AI approaches requires deep understanding of each system's capabilities and limitations. The research also reveals that while language model assistance can significantly improve planning performance, it introduces computational overhead and system complexity, requiring careful management. What makes this work particularly significant is its mature approach to AI system integration. Rather than simply replacing classical methods with modern neural approaches or dismissing neural methods as unreliable, the researchers demonstrate how different AI paradigms can be combined synergistically to achieve performance exceeding what either approach could accomplish alone. This represents sophisticated understanding of the AI landscape that recognizes the value of both established and emerging techniques. The research provides a blueprint for developing hybrid AI systems across many domains, with principles extending far beyond planning applications. The careful analysis of when different AI approaches are most effective, the sophisticated integration of symbolic and neural methods, and the emphasis on practical deployment considerations offer guidance for increasingly complex AI system development. This points toward a future where AI systems are sophisticated collaborations between different types of intelligence, like symphony orchestras combining instruments to create rich, complex music. Looking toward future directions, the findings paint a picture of a field becoming increasingly sophisticated in its understanding of intelligence itself. The research suggests movement toward an era of hybrid AI systems that combine multiple approaches to reasoning and learning. One promising direction involves developing adaptive AI architectures that can modify themselves based on encountered challenges. Rather than designing fixed systems handling all scenarios with the same approach, future AI systems may reconfigure themselves dynamically, allocating computational resources and selecting reasoning strategies based on specific situational demands. The research on evaluation methodologies suggests movement toward more sophisticated approaches to assessing AI system performance, with future platforms potentially integrating assessment into natural user interactions. This could lead to AI systems that improve continuously through deployment, learning from ongoing interaction with real users and applications. The findings about cognitive biases suggest future research may need to draw more heavily on insights from psychology and cognitive science. Today's exploration reveals a field that's simultaneously more promising and more complex than many might expect. The overarching message is that the future of AI lies not in any single breakthrough technology, but in our growing understanding of how to combine different approaches thoughtfully and effectively. Just as human intelligence emerges from complex interaction of multiple cognitive systems, artificial intelligence may achieve its greatest potential through careful orchestration of diverse computational approaches. These findings have immediate implications for anyone working with AI systems today. They suggest that the most effective AI applications will likely combine multiple approaches rather than relying on any single technology, that real-world evaluation is crucial for understanding true system performance, and that careful attention to bias detection and mitigation is essential for reliable AI deployment. The research reminds us that significant advances often come from deeper understanding of how to combine existing techniques more effectively. This research synthesis was created using advanced AI systems to ensure comprehensive coverage of the latest developments. The synthesis utilized GPT Anthropic Claude Sonnet 4 model from May 14, 2025, for content analysis and synthesis. Text-to-speech synthesis was powered by DeepGram technology to ensure clear, natural narration. Image generation was accomplished using OpenAI systems to create relevant visual content. All content underwent review by human experts to ensure accuracy and relevance, though some oversights may exist. Complete references to all original research papers are provided through academic databases. The goal is to make cutting-edge AI research accessible to broader audiences while maintaining scientific rigor and accuracy. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. If today's discussion has sparked your curiosity, dig deeper into these papers yourself through academic databases. Share your thoughts using hashtag AI Frontiers and let us know which aspects you find most intriguing. The conversation about AI's future affects all of us, and your perspectives help shape this crucial field. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by Archive Preprint Server.